Alright, so now we're going to be talking about work and reviewing work, doing some calculations. So, if we're talking about work, or if you have to calculate the work being done, it is the amount of energy being transferred. So remember, energy is not created or destroyed, it's just transferred from one to another. So, like we talked about potential to kinetic, or kinetic to potential. If you calculate the work done, you're calculating the force times the distance moved in the direction of the force. So you want the force and the distance to be working together, going towards the same direction. This is the equation that we'll mostly be using. Work equals force times distance, or displacement. So remember, force is measured in newtons, distance is going to be in meters, and now work, because we're talking about work, is the amount of energy transferred. Work is going to be measured in joules. All right, so here's some examples of no work, because really in real life you think, oh, if I'm exerting energy, I'm doing work. Well, not necessarily. So here's a man, he's holding a briefcase. You see the force arrow going up because he is holding it up. He's applying a force to hold it up. However, he's not moving. There's no distance being covered. So because there's no distance, there's no work being done. All right, here, you have that it's moving now, but see, our force is still holding that briefcase up. So notice how our force and our distance vectors, or our arrows, are not working together. So because they're not working together, we are not accomplishing any work there either. He's just carrying his briefcase. That's not considered work. So work could not exist, as we just talked about, or work could be positive or negative. So work is positive work, when you are lifting the box. So if you're lifting the box, notice how you have a vector force going upward, and the box is moving upward. Two arrows working together. Yes, you were doing positive work. However, work could be negative if you're maybe lowering the box. So if you're lowering the box, that's going to be negative. The force is still going to be upward. You're still holding that box up. You're just not using as much force to keep it up in the air. So the force is still going upward. However, the box is going down. So you are moving the box and you are applying force, but it's a negative work being done because your arrows are going in two different directions. All right, so if you need some visuals, sometimes you have to draw pictures with these examples. So if your picture indicates that the force is going upward and your displacement is going to a side, this kind of creates a perpendicular relationship. If force and distance is perpendicular, then the work done is zero. You have completed no work. Kind of like that guy who was holding up his briefcase and walking. No work was being done. All right. If your force is being applied to the right and your displacement being applied to the right, they're going in the same direction. Work is positive. Or it could have been work and displacement both being applied to the left. But as long as your arrows are going together, same direction, work is going to be positive. And then, of course, our last scenario, work can be negative. So work is negative when you have your force going one way and your displacement, or your distance that the object's moving, going the other way. That's negative. All right, so let's go over some examples in these different scenarios. So you have a girl in this top example, and she's pushing the box. Notice her direction of the force, the box she's pushing to the right. The direction of motion of the box is going to the right. So you have two arrows working together. Is she doing work? Yeah, she is. She is doing work, and it is a positive work because your two arrows are going together. She's actually doing work. All right, let's look at the girl over here. She's carrying a backpack. So her shoulders are keeping the backpack up. She's applying an upward force to keep it up with the tension of the strap. But she's moving. So the backpack is moving to the right. Notice the relationship of our arrows. One's going up and one's going to the right. So is she doing work? No. They have a perpendicular relationship. So because it's perpendicular, no work is being done. All right, what about this third example? You have a girl who is lifting something. She's lifting, it looks like a bag of groceries. So she's applying an upward force, and the groceries are actually moving upward. Is she completing work? Yes. Yes, she is. And notice, again, our arrows are going the same direction. So this is going to be positive work. All right. What about in our last example? You have a girl, she looks like she's just carrying the groceries. So she's using an upward force to keep the groceries up in her arms, but then she's walking to the right. Is she doing work? No, she's not. Again, it's a perpendicular relationship. Force and distance are not going the same direction, so no work is being done. All right, so to calculate work, we're going to do a couple of calculations. So as you can already see, work has a special meaning in science. When we're talking about work in science in our physics class, we're talking about a force being applied and an object moving in some sort of distance. And they need to be going in the same direction. Or if they're going in opposite directions, maybe a pulley system's involved, it could be a negative work. But remember, if you have a force going upward, and the distance is going to the left or the right, remember that is no work. You can't have that perpendicular relationship. So we're going to be using this equation. Work equals force times distance. So remember, work is in joules, our force is in newtons, and our distance is in meters. All right, if you need to write down that equation, go ahead and do so. We're going to do some practice problems. All right, number 1, a book weighing 1 newton. So 1 newton, that's its weight. So that's a force of weight is 1 newton, and it is lifted 2 meters. So that's a distance or displacement. It's lifted up 2 meters. How much work is being done? All right, so we need to find work. We know that work is force times distance. So work equals, our force was 1, and our distance was 2. So the work being done was 2. Remember, we're talking about work here. Work is measured in joules. So you should have gotten 2 joules. All right, number 2, a force of 15 newtons. So the force is 15 newtons, and it's used to push a box along the floor a distance of 3 meters. Distance of 3 meters. How much work was being done? So we're looking for the work again. Work equals force times displacement or distance. So work equals, our force was 15 times our distance was 3. 15 times 3 is 45. And again, we're talking about work, so it should be 45 joules. All right, number 3. It took 50 joules. All right, 50 joules. All right. We could be talking about energy, we could be talking about work. To push a chair 5 meters across the floor. So our distance is 5 meters. So we're talking about 50 joules of work. We accomplished some sort of task. Something moved when we applied a force. So the 50 joules is work. We know that the distance was 5 meters, and we want to know with what force. So now we're looking for the amount of force that was used to push that chair. So we're doing work equals force times displacement or distance. All right, let's plug in with what we know. So we know that the work done was 50 joules equals, well, we're looking for the force, so F times the distance is 5. So we need to get F on a side by itself, figure out what that force is. So we need to divide by 5, cancels on this side. 50 divided by 5 is going to be 10 equals F. And we're talking about force, so it's 10 newtons. Or number 4, a force of 100 newton. So number 4 says a force of 100 newton. So F equals 100 newton was necessary to lift a rock. All right, so we're lifting something. A total of 150 joules of work was done. So 150 joules of work. So we know our work was 150 joules. How far was the rock lifted? So we're looking for the displacement or the distance. So work equals force times displacement or distance. We know that the work was 150 equals 100 times d. We need to know what the distance is, so we need to divide by 100, so that way we can get d on a side all by itself. What we do on one side, we have to do to the other. All right, so we should have 150 divided by 100. The two zeros can cancel out. So essentially we have 15 divided by 10. That should give us 1.5 for our distance, and it's 1.5 meters. So that's how far the rock was lifted off the ground, about 1.5 meters. All right, so number 5. It took 500 newtons of force, 500 newtons of force, we know our force is 500 newtons, to push a car 4 meters. All right, so that's our distance. Our car has moved 4 meters. How much work was done? So we're looking for work. We know work is equal to force times distance. So work equals 500 times 4. Well, 5 times 4 is 20. Add these two zeros back in. So you should have 2,000. And we're talking about work here. So 2,000 joules. Number 6. A young man exerted a force of 9,000 newtons. All right. So number 6, a force of 9,000 newtons was applied on a stalled car, but was unable to move it. So our distance was 0. How much work was done? Work equals force times distance. Well, if we want to know our work, we need to plug in our force was 9,000 times our distance. Car didn't move, 0. So our work was 0 joules. It didn't move. No work was done. You may feel like you worked because you pushed on that car, but you didn't move it, so no work was done. Number 7, a woman carries her 5-kilogram purse 20 meters. So we know a distance of 20 meters to go to the mall. She uses 10 newtons of force, 10 newtons of force to hold it on her shoulder. How much work did she do? All right, so keep in mind, she's holding it up on her shoulder with 10 newtons of force, and she's traveling 20 meters. So this is that perpendicular relationship. Is she doing any work? How much work did she do? None. Because technically, her force and her distance were two different directions. A perpendicular relationship means no work was done. No math had to be done because she didn't do any work. All right, that concludes our work lesson. Next will be power. Thank you.